The following is a presentation of the Six Arrows Radio Network.
This week on the Workbench, all about oscilloscopes, Part 2. Stay tuned. Welcome to the Workbench. I'm your host, George, KJ6VU.
And I'm Jeremy, KF7IJZ.
The Workbench is sponsored by CADsoft, makers of Eagle PCB design tools. Get your free copy at cadsoft.io. And by MCM Electronics, where I can and you can buy all of your electronic parts needs and equipment. Check out mcmelectronics.com today.
Welcome to episode 6 of the Ham Radio 360 Workbench podcast. This week we're going to be continuing our conversation with Alan, W2AEW, about digital oscilloscopes. Last time we went in depth on oscilloscopes in general and really kind of focused on analog scopes and their utility, and we kind of covered accessories like things like probes.
And if you're new to the Workbench, we wanted to kick off a series of podcasts really focusing on technical go deep topics in amateur radio. The whole idea was really to encourage more hands-on, more building, and really getting to understand electronics and relevant technical topics to ham radio. And up to now, we've had episodes touching on many of the basic setups to get your Workbench configured right. The bench itself, hand tools, power supplies, meters, and in the last episode, the first part of our oscilloscope series. And as Jeremy just mentioned, today is part 2 of that series. In addition to that, over the next few episodes, we're also going to start to get into our first build project, our antenna analyzer. We'll talk about that a little bit later in the show.
Why wait till later?
Why wait till later?
We keep teasing this project, and I know that I get contacted constantly from people saying, when's it going to come out? I want to go buy an analyzer, but I really want to wait and see what you guys are going to do. Do we have any meaningful updates this week?
Well, we have some progress, yes, and we're still pretty much on the original schedule. So what's happened over the last couple of weeks is that we received our final version of the printed circuit boards to test. So we've got the boards, we've got the parts, we've populated the boards, and Barrick, who's the designer of the circuit, is testing the boards with the latest component selection so we can finalize the bill of materials. So once that's fixed, then we can figure out how we're going to get the kitting and all that done. So we're basically in final design testing at the moment, and hopefully that'll wrap up in the next week or so.
And the other good news is that things are looking better and better about actually being able to get fully parted out kits rather than having folks having to source every single piece themselves. This is something we're working on behind the scenes. I can't guarantee that it's going to come together yet, but it is something that we are making good progress on. And I think we've finalized the bill of materials, right?
We do have a final bill of materials that we're working with right now, and unless we find something strange in the design of the circuit when we test it, then yes, our bill of materials is fixed at this point. And
to really wet people's whistles on this build project, are we going to have Barrick join us sometime in the near future?
Yes, we are actually in 2 or 3 episodes out from now, probably 3. We'll have him on the show, and in that episode, what we're going to do is walk through the circuit, talk about what the thing does, how it works, what some of the key components are, and how you would go about building it. And of course, at that time, we would also announce exactly how you could order a kit and who you would order it from and what you'll get.
So just remind the listeners, George, what is the frequency range of this analyzer going to be?
Well, the original spec was HF, so 3 to 30 megahertz. And it turns out the synthesis chip that we're using in the design is good from 0 to 40 megahertz. I suspect there's some roll-off closer to 40, but so it well covers the HF spectrum. We have also looked at other digital synthesis chips that are actually good up to about 150 megahertz. So we might do another version down the road a bit that would actually take it up into the 2 meter spectrum. But the first version will be HF.
Okay, and I think one thing that would be really helpful from you, our listeners, is if you have, heard about this and it's something that you're interested in, I would love if you could email us at workbench@hamradio360.com. Let us know that you're interested and give us a rough idea of what price point you would like to see. It's just good to get this feedback. Obviously, we can't guarantee anything at this time, but it would be nice to know what our listeners are thinking about.
And of course, our goal in this is to make it as inexpensive as possible. So we have to source all the components and the little sub-assemblies, and we're shopping around to try to find the very lowest prices. So the idea really is to deliver a kit of parts that is essentially at our cost. We're really not, this is not a business by any stretch of the imagination. So the whole idea is to source the parts and pass that along to the listeners just to cover the cost. The other thing that I'll mention is the big question for us is how many kits to make. Because if 5 or 6 people say, would love to have this, we can't really go out and make 200 kits. So the more people who respond to your question, Jeremy, the better, because we'll have a sense for the number that we'll need to make. Because once you start the process, you don't want to have to do it over and over again. So we'd like to be able to capture the number of units people want.
And to that point, we don't know ultimately how many runs. This may be a one-time thing. If there's enough demand for it, we may see multiple runs. But again, still very preliminary. We're trying to figure these details out. So if you could drop us a note about your interest at workbench@hamradio360.com, or you can tweet us. I'm at KF7IJZ.
And I'm George at hamradio360.com or at KJ6VU on Twitter.
Yeah, just reach out. You can post in the Ham Radio 360 Facebook group. We monitor all these things. It would help us get a good idea of how many folks are actually interested. So sorry to put you on the spot, George, but I felt like we just really owed people some more information because we keep talking about it. I promise it's coming. I have seen things. They are real.
Yeah, actually, the photographs that we've been posting on my blog site and also on the Ham Radio 360 Facebook page will show you what the prototype looks like, and the final unit will look pretty much the same. The only potential changes might be a component change here or there, but it'll be largely what you see in the photograph.
All right, so this week in news, it's actually, I don't really have much. I did want to comment on the Kenwood THD74 that we spoke about, I think, 2 episodes ago. Mm-hmm. So, of course, the THD74 at this point has been announced. It should start shipping. I've heard everything from September to November. I'm believing more likely closer to the end of September. The radio will be selling for street $650. And one of the things that has been lacking is that, as far as I know, there's no manual out there. People have a lot of questions, and there haven't been a lot of answers. One thing I have come across on YouTube, there is a ham. His name is Don. His call sign is Whiskey 6 Golf Papa Sierra, so W6 GPS. A lot of you may know Don from his involvement with the AvMap GPS units that plug directly into Kenwood radios and offer you APRS mapping and messaging capabilities from their GPS units. They're actually quite nice for having kind of a not quite an all-in-one, but I mean, it's a nice package when you put the things together. But anyway, he was given an early unit and has been doing quite a number of videos on YouTube, actually walking you through setups. He's done a couple of interviews with folks answering some questions, and so we'll put links to his channel in the show notes so you can go check that out if you are interested. As far as following up on the ICOM ID51 Plus 2, other than the fact that it has been announced, and I have noticed actually ICOM is giving those away as prizes for the upcoming D-Star QSO party, which I think is at the end of September. I think it's the last weekend. But I haven't seen any information about those being available for sale or any information about pricing. So as soon as we know something, we will bring it to you.
Hey, I've got a question for you on the Kenwood. So 650 is pretty steep for a handy-talkie. And I know it's got a ton of features, but when you looked at it, what was your impression of the set of features versus the price?
I'll say this. So if I remember correctly, when I bought the first ID51, I think I paid $600 for it. It wasn't necessarily completely revolutionary, but it was pretty awesome. as far as the features, the way that the DR, which is the automatic using the GPS to find local D-Star repeaters, and now in the current version of the radio, analog repeaters, which is kind of a no-brainer in 2016. I feel like 650 is probably a little bit expensive, but somebody did, I can't remember where I heard this, but somebody kind of did put it in perspective for me. And I know I've seen a lot of people being like, oh, my Yaesu whatever in 1982 cost X number of dollars, which when adjusted for inflation is like $800 today. That's fine. But we live in a world where, you know, the flood of Chinese HTs have really cut the bottom out of the low-end market. And of course, there aren't any Chinese HTs with APRS or D-Star that I'm aware of. But I would have loved to have seen a $599 street price. I feel like that would have been conversationally tolerable. But as somebody pointed out, if you want to go buy a THD72, which is their current APRS only handy talkie, I think those are still selling for like $450 or thereabouts. So effectively, if you wanted to add D-Star, you could go pick up an ID51 for anywhere from $250 to $350, depending on what model. And when you put those two things together, as far as having two separate radios, then, okay, you're kind of getting in the price range where $650 is a bargain for two separate radios to give you that capability. So, George, yeah, beat you to it.
Yeah. Go ahead. What were you going to say?
What do you have on your workbench this week?
We've been trying to get these Pactena antennas made, and we finally kicked off a build of the classic Pactenas. The wire antenna element assembly is done, and the assembly house that does that work shipped them all back to me. So I've got a huge pile of link dipoles all wrapped up on winders. And the next thing is to get the one-to-one Ballon feed point done, and I got all the circuit boards in. Actually, yesterday they showed up. I need to take those things over to that assembly house. It's a different company that does that. So those will go off, and probably in a couple weeks, everything will be done, and we could bag them up and start shipping them out. So we're pretty excited to get them going.
Just in time for the holidays.
Just in time for Pacificon here in California. So we hope to have them by Pacificon. So we'll have something to actually take there and show off. So yeah, there's been quite a bit of interest in them, and it's great that people want more. So
speaking of Pacificon, I think you have another announcement.
Oh yeah, so I'm doing a presentation at Pacificon, and it's all about portable HF operating tips. So the idea is, if you're interested in doing HF portable for SOTA, for example, or you could apply this thinking to travel, like I'm going to go on a car trip and what would I take? So I'm going to break down ideas about radios and antennas and batteries and accessories and all that. And the approach that I'm taking is kind of a practical guide to this. So some of the things that we're going to look at are things like comparing radios and looking at the size, the weight, the functionality, essentially the bang for the buck or the bang for the size or the bang for the pound, and compare some of the different radios, do the same thing with batteries, do the same thing with antennas. And one thing that was really exciting to me is your BioNO battery analysis project is a perfect feed to this topic. So I'm going to plagiarize a lot of your good work around analyzing the different battery types and the characteristics for discharge, so that'll factor in on the battery side very heavily on this presentation. So thanks for that. That was really awesome.
Well, I think you should think of it less as plagiarism and more as my opportunity to attend Pacificon in spirit, because I've always wanted to go to Pacificon. It's just not in the cards anytime soon. So I'm glad to know that if I can't be there, my data can.
Your data will be there, and it'll be well received. So what's happening on your bench?
Well, I think I actually want to talk more about what's not happening on my bench. So, I can't remember what day last week, but I was on the floor actually digging through a parts bin that I have under my desk. And as I triumphantly found the thing for which I was looking, I took a look up, and there was a blinking red LED on my desk. And this blinking red LED belongs to my Hakko 888 soldering station. What the blinking LED indicates is that the iron is at temperature. In this case, I had it set to 750 degrees Fahrenheit. And that's great. except for the fact that I had not used my iron on anything in 2.5 weeks. So I had a soldering iron on my desk running at 700 plus degrees for 2.5 weeks. And I am so thankful that I did not find a fire on my workbench.
Wow.
Yeah, I mean, actually, it really shook me up the rest of the night because that I could be so careless. Like the last time I used it was to repair the loose power plug on the charger for the Titera MD380. I had to just reflow some solder basically to fix this cold solder joint, and that was the last time I'd used it. And I put the pencil back in the holder and I just walked away, completely absent-minded about flipping that switch. So I've been researching irons that have automatic, shutoffs that can detect through sensing in the holder, like in the cradle, they can detect whether or not you're still pulling the iron in and out. And if you don't touch it for 30 minutes, they shut off. There are some Hakos in the $250 to $300 range where you start to be able to find that. But then I've also found a Weller that I think was about $149 that has that feature. So I am in the market for a new iron because my old iron is now black and crusty on the actually heating, like the shaft of the pencil, and then the tip is completely carbon.
So was this a station or a pencil?
It's a station. So
okay. So can't you just replace the heating element or the tip or whatever? It got kind of ugly.
I could, except that I also noticed a very loud buzz coming from the main body. So I haven't turned it back on since then. For all I know, maybe the body is still fine, and I just need to replace the actual soldering pencil. But I haven't even seen those available for sale. That's something I do need to look into.
So my advice is that while you have this frame of mind, you need to buy the new one now. And then in a month or two, you need to test the old one to see if it still works. Because at that point, if it still works, well, you got two.
Yes. And that's not bad. Maybe what I should do is mount the burnt soldering pencil in a shadow box and give it away to our listeners as a cautionary tale. I've actually also been looking at some of the microcontroller controllable AC switching things out there to see if I can roll my own with like an Arduino as far as automatically determining to shut the iron off after a certain amount of time.
I can tell you how to do that, I bet.
Well, maybe we'll do a show on it. I have a good idea, but yes, I'd love to talk about that further. Two other things I've had on the bench. One is incredibly frustrating, but very simple. I have a 2013 Honda Pilot that has parking sensors, which are very handy, little ultrasonic distance sensors that beep as you get closer to stuff that keep you from running into things. And we were getting an error code on the information display saying they weren't working. Well, after doing some Googling, apparently having a $5 light bulb behind the button burn out will actually disable the $1,200 parking sensor system. So, we pop the switch out. There are two bulbs in the switch, one to indicate that the thing is on and off, and one to illuminate the symbol on the button. While we're waiting for that part to be handmade, apparently, because it's been 3 weeks and it still hasn't come in, I just swapped the bulbs around, and I had the old bulb just making sure that it was, in fact, burned out. And it was incredible. Like, that's really bad design, that a $5 bulb burning out disables a good safety system. So a little frustrated about that. And then the last thing is that I finally finished part 2 of my Raspberry Pi cluster videos, focusing on how do you configure the software for the Zero node to act as the DHCP and NAT server, and how do you get Einstein and Home up and running on all the nodes in the cluster.
Oh, cool. So actually, do you have Einstein running all the time now?
Oh, yeah. I've got 2 clusters. I actually lead a team on Einstein and Home called Raspberry Pi, Raspberry Space Pi. My 2 clusters in total, since I started contributing in April of last year. I have over 1.3 million credits now, and my rack is over 7,000. It was actually up over 8,000, but I had a Pi cook itself when a fan died, which I mentioned the last time we did this segment. But what's actually really crazy to me?
What's that?
My first video, maybe even by the time this episode airs, will have had 100,000 views, and it just amazes me that some hayseed from Ohio put something on the internet that has been seen 100,000 times.
And they're not just pointing at you laughing.
No, a couple of them are. Apparently, I mispronounced the word spudger, which is a plastic pry tool. I pronounced it spooger because that's what I'd always heard it called. But anyway, I pronounced it spooger, and I've had a lot of people come in and comment and leave some inappropriate video links to poke fun at me.
You're right. It is spudger. I used to think it was a spludger.
Nope, spudger.
I'll be darned.
Yeah.
Well, that's cool. So what, by the way, on Einstein at Home, what sort of calculating is being done? What's the purpose of that?
So it uses fast Fourier transform math to take raw data from, I think in my case, it's the Arecibo radio telescope, and it runs algorithms on it to determine, basically to look for signals above the noise floor by running the fast Fourier transforms on it. And it is currently, the work units that my pies are doing are all centered around finding binary pulsars. In theory, so one of the project leads for Einstein at Home is actually a member of our Raspberry Pi team, and he actually had the gravitational wave search running on Raspberry Pi, and we've been trying to get him to release that to the public. But it requires a special kind of user who actually pays attention to whether or not machines in their farm are down or not. Otherwise, the results aren't very good because it takes like 6 days to finish one of those. Whereas my little Core i5 Intel NUC that's 2 years old was doing a gravitational wave item in about a day.
So it's actually really useful. This is not just some hacky hypothetical project.
No, it is useful. I mean, and this whole thing started for me because, again, I didn't have a good practical application for playing with Raspberry Pi. I didn't want to build something that like monitored how often my animals were eating. And so I was like, oh, it's a tiny little cluster. So effectively what I have built is a 32-core machine where every core has a 1/4 gig of RAM available to it, which is pretty cool. One of the next challenges I may take on is start to use Docker, which is a containerization technology to actually build some applications on just to play with.
Wow, that sounds awesome.
Yeah,
congratulations. I think that's really cool.
How many 32-core computers do you have?
Let's not go there.
So yeah, before that's it for the Workbench. But before we jump back into oscilloscopes, I want to remind our listeners again that for any of your tool needs, your project needs, your component needs, Raspberry Pi, Arduino, don't forget to check out our sponsors, MCM Electronics at mcmelectronics.com, where you can save 5% off your next order with the code RADIO5. That's Romeo Alpha India D.
You can run Einstein at Home, but you can't spell radio.
Well, in phonetics, it's RADIO 5. Radio 5 will get you 5% off your next order at MCM Electronics.
All right. Beep.
The Workbench is sponsored by our friends at CADsoft. You know, they're the makers of the Eagle PCB design software, the very software George used to design the Pactena Classic, Pactena Mini, what him and Barrick are using to create this new antenna analyzer project for you here on the Workbench. You know, they got hundreds of parts libraries, tons of reference designs, and a monster huge user community. Eagle's a great choice for your next ham radio project, and you can get your free copy of their software today. Click on over to cadsoft.io and start getting your project put together today.
Well, here we are back for part 2, still with Alan, W2AEW, from Tektronix, which is actually really awesome because who better to have to talk about oscilloscopes?
Well, I'm glad to be back. And it's kind of like the trade-off between, a Dave Jones 1-hour video on scopes or a W2AEW video that is usually about 10 or 15 minutes. So it's kind of the same thing.
Well, and you speak the right kind of English. That helps too.
Okay. No crikey or Bob's your uncle or all that stuff.
For those of you who don't know, we're talking about Dave Jones from the EEV blog and the EEV blog forum. And Dave was instrumental in me personally because I stumbled upon him accidentally, and he was the one who made me realize that digital oscilloscopes were within the realm of affordability for a hobbyist. Talking about the Regal $400 scope, which was really popular a couple of years ago. And of course, they still sell them, but they've gone on. You can now actually get a 50 megahertz 4-channel scope from them for $400, which is absolutely insane. And in this segment, we're really going to focus, we covered a lot of overall generalities about oscilloscopes. We talked about probes. We went in depth on analog scopes and why they're still useful. But there's a lot of stuff that digital scopes bring to the table that analog scopes did not do, and that's where we're going to pick things up. So, Alan, why don't you kind of give us an overview of, in addition to just being able to render signals, what are some of the other things that digital scopes bring to the table?
Wow. Okay, big topic. Oh, we'll kind of try to overall nutshell of it here.
Well, if you think there is a better way to organize that, you can reframe my question in the form of your own question, because again, you're the expert.
Yeah, let's just kind of start. What does it bring? Compare and contrast. And like I said, the analog scopes display you a waveform on a very temporary surface, right? You're illuminating some phosphor on a CRT face that fades away very quickly. Okay, a digital scope essentially samples the waveform, takes pictures of it, if you will, takes samples of the voltage, and puts it in memory. And now it's there in perpetuity for you to do something with. Oftentimes it's just a display on the screen, and then maybe you'll retrigger and get another trace. But you have the option of saying, well, just grab one acquisition and show it to me. Let me go zoom around on it. Let me study it. Let me make automatic measurements on it. What's the frequency? What's the amplitude? You can do all these things automatically because you have essentially taken a picture of that waveform, actually many thousands of little pictures of voltages over time. And then the scope can do all kinds of processing on that. You can output those waveforms to your computer. You can do other things with them. So it really brings the scope to a completely different level in terms of what you can see on these waveforms, what you can measure on them automatically without you having to do, any counting of divisions or anything like that. So, with that capability comes other things that we'll talk about in this episode, of considerations to think about, like sample rate and memory size and sampling modes and other things like that can become important when you go start using a digital scope and want to understand what it's doing for you and to make sure it doesn't lie to you.
All right. So at the very basic, when we start talking about basic additional functions, in addition to actually just drawing the waveform on the screen, you talked about kind of capturing that. Talk about a little bit, how does that manifest itself in the controls of the scope? What do I do with something that I've captured?
Well, generally you're going to drive the basic controls of the scope, the triggering, the three basic areas, the vertical sensitivity, the horizontal scale, and the trigger controls. You're going to largely drive them the same way as you would on an analog scope. But at the end of the day, what the hardware is doing is taking voltage samples over time to build up that waveform that it sticks in memory. And then inside the scope, it takes those voltages and translates to a visual waveform on the screen for you. Because the waveform is essentially saved, even if it's just for a moment, it's saved. The scope itself can actually make automatic measurements for you. It knows how to make things like an amplitude measurement, or a rise time measurement, or a frequency measurement, or a period measurement, because it is just doing mathematical processing on those voltage samples over time. Oftentimes you can then, once you've got a waveform captured, you could zoom in on an area of it to look at a little anomaly or a little disturbance on a waveform. If you're looking at, say, a digital waveform on an I2C bus or an SPI bus, and you see a little disturbance on the rising edge, like maybe a little bit of ringing on the waveform, you can zoom in on that and see, does the ringing dip down below the logic threshold? Is that going to cause me a problem? By being able to kind of stop, pause, and zoom, on things like that, it makes it very easy to kind of dig in and look at some details that might not be so obvious if you were just looking at the 50,000-foot view of that particular waveform.
Well, so you actually bring up an interesting point, because we're talking about you're capturing, and I'm going to call it an event or the waveform into memory. Am I able to, once I've captured that, in other words, I've captured the signal in the representation based on how the scope is set up as far as sample rate and depth and everything. Am I able to get back at that and actually zoom in and zoom out?
In most cases, yes, but there will be limits to that. And it really kind of gets into how you've set the scope up in terms of how much memory you've allocated for a particular waveform, because there are a couple of things that are kind of intimately tied together. One is sample rate, the memory being used, and the horizontal scale being used. Because let's say I set the scope to, a millisecond per division. So that means I've got 10 milliseconds represented across the screen. If I've chosen to use, say, 1,000 sample points, that's going to basically, now I've divided 10 milliseconds by 1,000. So my interval from one waveform sample to the next is just that 10 milliseconds divided by 1,000, or 10 microseconds. So that essentially sets the sample rate of that waveform. Now, you might choose to, some of the scopes will allow you to say, oh, don't use 1,000 points, but use 10,000 points or 100,000 points to represent that waveform. So now the effective sample rate of that waveform will be higher, because now I've taken that same 10 milliseconds, and instead of dividing it by 1,000, I've divided it by 10,000 or 100,000 points. So my time interval from one point to the next is now smaller. And the amount that you do that will be, largely determine how far you'd be able to zoom in to look at a detail of a waveform. Make sense?
Yes. So in other words, how you have the scope set up when you're capturing can influence how much or what resolution of data is captured, but then there's also the opportunity potentially to set settings beyond just what you're seeing on the screen to capture more data than you're actually looking at. And if you're able to do that, then it sounds like you may be able to examine the wave in more detail if your scope allows for that type of feature.
Right. And there's also other things that can get into this. I mean, so memory is important to think about, and how your scope allows you to manage that memory / sample rate for a given, horizontal time-based setting. The other thing to think about is something called the sample mode that's in, although it's something you want to talk about now or move on, but that can also influence, what is represented in that particular waveform. Okay, so let's say I've got a scope that can sample at, a gigasample per second. Okay, and the particular set of settings that I have, are going to result in a waveform whose waveform sample rate is only, say 100 megasample per second. That means the scope can sample 10 times faster than this waveform needs. Okay? So what does the scope do? Generally, the scope is not going to simply reduce its sample rate. It doesn't adjust the sample rate of the analog to digital converter. It's still sampling at a gigasample per second. But what it's going to do is it's sampling 10 times more points than it's actually going to use in the waveform that you're storing, because of maybe the settings that you have set up. Okay, because maybe you don't need the full gigasample per second. So normally what the scope will do, it'll be in what's called sample mode, where it may take those 10 points and only pick one of them that's going to use in the waveform and throw the other 9 away. And then takes another 10 and then picks one of them, throws the other 9 away, and keeps doing that. So that's how it decimates the sample rate, by just throwing away the samples that it doesn't need to represent the waveform the way you asked for it. So and that's okay. Go ahead.
So this is interesting because, for those 10 samples, in other data sampling modes, you might call that a frame. But I would assume the scope would take those 10 points and kind of average them together to get the point, not just randomly pick one according to an algorithm and then throw the rest away. So that's kind of surprising.
So, that's a great point. So now that you understand that that's really what the scope is doing, because oftentimes the display of the scope will tell you. I mean, most better digital scopes will tell you for a given horizontal scale setting and a given memory setting, it'll tell you on the screen what the sample rate is of the waveform that you're looking at, and it might not be that maximum sample rate. And it got to there by doing some decimation somehow. And so the sample mode is the way that by default most scopes work. And it usually is it's like the first point of that frame, if you will, or the second, the first point of the next frame, first point of the next frame, and the rest are just ignored. There are other sample modes. There's one called a peak detect mode. What the peak detect mode is, it looks at all of those samples that are in, we can call it a frame, but I would call it like a waveform point interval. Okay, maybe those 10 points. It will pick out, say, the highest one and the lowest one, and then draw essentially a very narrow vertical bar on the waveform to show you the excursion that occurred during that time period. So instead of getting a nice thin waveform, you might get a kind of a little bit of an envelope around the waveform showing the peak variation that occurred, at each sample point. That's called a peak detect mode. There's an envelope mode where it does that and keeps doing that on repetitive triggers. So overall, over time, you can see the peak excursion that occurred on that waveform at each point in time. So those are not used that often, but they can be useful, particularly when you're dealing with something where you're close to the Nyquist for RF, and you're trying to look at an RF envelope. That peak detect mode can be helpful in those situations. And like if you play with your Regal scope, Jeremy, to look at the modulated RF output of an HF single sideband signal, you might find that the peak detect mode will do a better job than the sample mode. Now, many scopes, and not all, but many scopes will do what you suggested when we first started talking about this, is taking that group of points and averaging them all together to a single point, and then moving on to the next sample interval, taking that group of points and doing what we call an in situ average. Tektronix calls that high-res sampling. It's a high-res sample mode. And it actually is really interesting because not only does it give you maybe a better representation because you're essentially averaging all the points that would fit in that where that one waveform sample or display point is. But each time you average samples together, you actually improve the resolution. Right? Most of these scopes that use an 8-bit analog to digital converter, so you have essentially one of 256 values. But each time I take two 8-bit samples and average them together, I gain another half a bit of resolution. Okay, so this in situ averaging from high-res sampling actually improves the vertical resolution and also does a little bit of low-pass filtering. So it can make a very, very sharp waveform. It does require that the scope hardware has the ability to do this in situ averaging quickly enough to not dramatically impact the waveform capture rate. Okay, and there's some processing involved in doing this kind of floating point averaging of these sample points, but that would typically be called high-res sample mode. At least that's what Tektronix calls it. I've never used one of the Regal scopes, so I don't know if they've got an equivalent function. But you might want to take a look and see, what acquisition or sample modes the scope has, and play around with that. But so you really have to think about what's the processing, from the raw sample rate to the waveform memory, and then also if the waveform memory was 100,000 samples or 1,000,000 points, you don't have that many pixels across the screen. So there is another data reduction of some form that has to happen between the waveform memory and the actual display memory. So there is a signal processing path there. And again, I did a video on this too, to kind of really explore what's going on with all of that. And there's a lot of subtleties in there that, when you really start thinking about it, can really affect what that signal looks like when you start capturing it and then zooming in on it.
Now, back to your point, the Regal that I have, which is a 1000 series, 1000Z, it does the normal acquisition, which is basically capturing the raw data. It does the peak detect that you mentioned. It has an averaging mode, and you can set how many samples are averaged together to build a data point. And then it also does have that high resolution mode that you mentioned, although it probably works a little bit different than the higher end tech scopes.
Well, I just want to stop here a sec. The averaging mode that you mentioned is a little different. That averaging mode and the high-res mode are different. The high-res mode will work on a single shot, right? Because it's taking a group of points and averaging it to 1 point on a single acquisition. Whereas the averaging mode takes multiple waveforms from subsequent acquisitions and averages those waveforms together.
It's funny you mentioned that because I have the manual open here and it says, note, average and high-res modes use different averaging methods. The former uses multi-sample average and the latter uses single sample average.
Okay, there you go.
What's interesting is, talking about this averaging mode, this sounds like the scope that you were talking about in the last episode that is incredibly wide bandwidth, but it takes a series of multiple sweeps and builds, a high-res image of the waveform over time.
Yeah, so the sampling, the equivalent time sampling scope and sometimes they're called random equivalent time or just sampling scopes. They typically use a much higher resolution converter because the sample rate isn't as high. It might be 100,000 samples a second or 200,000 samples per second maximum. But what the scope can do is very, very precisely place where it's making that sample with respect to the trigger. So by very precisely doing a sample and hold at a very precise time with respect to the trigger, it can use a 14 or 16-bit converter to get that value, where it's difficult to make a 14 or 16-bit converter that runs at a gigahertz. Okay, so you can look at extremely high frequency waveforms because it's all about the performance of the sample and hold and that delay generator. Okay, and then once you've done a sample and hold and a proper delay, now you can take your time in sampling that with a higher resolution converter because you're just going to process that one sample only and then get another trigger and grab one more sample. They work, one of two ways. One is where the actual sample and hold is driven with a delay circuit very precisely. Another one is where the sample is kind of free running, and each time a trigger occurs, the scope knows where those samples were grabbed with respect to that trigger and can place them properly on the screen. But at the end of the day, these things work by having a very precise sample and hold and timing measurement to the trigger to build up a waveform over many, many, many trigger events. Whereas what we've been talking about all along here have been scopes that sample very, very quickly, so you can do a single shot capture of a waveform based on one trigger event.
You keep mentioning single shot capture, and that's, I think one of the things that there are other modes as far as you can leave the scope just running and it will continuously process data as it sees it, or in the event where you're going to play, say you have a microcontroller and you want to capture sending some type of signal out of it that runs in a sequence. It has a very defined beginning and a very defined end. Like my Regal has the ability to just capture a single run based off of a trigger, or it can continuously capture data that you can either tell it to stop after a certain event has occurred, or if you manually were to press stop.
Yeah, or oftentimes there'll be a single button where you can, say, press single button, arm the trigger. As soon as the trigger occurs, capture the waveform and stop. So there's a couple of ways of making it stop. So just about all digital scopes have the ability of doing that. And that could be really handy, like you said, if you're dealing with, a serial communication, you want to capture that word, that sequence of pulses, those sequence of data that was sent from your microcontroller to your display or whatever it might be, or like I said, trying to capture the NEMA, data stream from your GPS unit to your Arduino or something. You can. It's like, it's essentially a recording. You're doing a recording at a particular point in time, capturing that data to do further analysis on it later. And that's really one of the defining beauties of a digital scope over an analog scope.
Now, we kind of hinted at this earlier. You were talking about getting, peak-to-peak voltage or rise time in some of these measurements. Can you talk a little bit more about, because this is the base layer of indication that the scope gives you before you get into advanced functions, but what are some of the data points that you can actually have the scope calculate and measure for you and display on screen?
Well, again, that's going to vary a lot by, scope to scope and manufacturer to manufacturer. Oftentimes, you're going to have the digital scopes because you're looking at effectively a computer display as opposed to an analog scope where you're just simply looking at traces. So there's a lot of information on the screen. There'll be a text readout of the number of volts per division. There'll be a text readout of the number of microseconds or milliseconds per division horizontally. They'll usually tell you what the sample rate is of that waveform, how much memory is being used. You can bring up cursors, like little markers, and move these cursors on the screen or across the waveform to make voltage and time measurements and voltage and time difference measurements, at any point on the waveform, because the markers or these cursors that you move along can just be positioned anywhere on the screen, and you get a readout of those things as well, even before you turn on like an automatic measurement. So, and then, the basic measurements we mentioned, like frequency and period and amplitude and peak-to-peak voltage and things like that. These, basically all analog scopes have those. But depending on, some scopes have, 20, 30, 40, 50 different measurements that you can make, and 90% of which none of us will ever use, but they're there. So it all depends on, what you're working on and whether that particular application is important to you or that particular measurement is important to you.
So, George, can you add any color as far as the common measurement types that are going to be useful for a ham?
Well, I think that this is probably the area that makes the digital scopes in a way the most attractive. When I first started using a digital scope, I could pop up on the screen several automatic measurements, like Alan was saying, and that was really kind of eye-opening for me because right away you could measure either the voltage or an average, an RMS value. Just it's all right there, and so that was actually very useful. Something I never would have seen on the typical analog kind of low-end oscilloscope. Suddenly, all these features are there in the digital scope, so that was really a big plus. But I think mainly just a voltage measurement, frankly, is very useful, or frequency measurement is very useful for most of the applications I've done, which is typically audio. I mean, I've done some digital stuff with the scope, but a lot of my scope work has been audio, and that's the things I found useful.
Let's talk about that just a little bit. I mean, I know we're kind of jumping from features to applications, but we mentioned audio as a use case for these scopes a lot in the last episode, and one of the things that oftentimes you will see in a specification, say for an audio amplifier, is they'll talk about total harmonic distortion, or they will talk about other characteristics measured at 1 kilohertz, which obviously if I have a signal generator that can pump 1 kilohertz sine wave into a system of some kind, be it an amplifier or whatever, that's very clearly a periodic wave. It's a 1 kilohertz sine wave. It's about as vanilla as it gets, which is a lot different than if I'm playing, the latest music from whatever band that I like, right? That's a complex, maybe calling it a complex waveform is incorrect, but it's not periodic. It's not something that looks like a sine wave, right?
You're right. You can certainly look at audio like that and you'll just see looks like a randomly varying thing, but obviously the higher the pitch of the sound, the faster the signal's going to be moving up and down on the screen compared to a low frequency signal that's going to vary more slowly across the screen. So, but it's just a combination of all these frequencies kind of all represented in one particular waveform. It's just that's the vibrations that are sent through the air, and you're just seeing those things represented as voltage. But for even things like you mentioned, doing like total harmonic distortion, that is something that you can get into with scopes like this. I mean, most of the scopes won't have a measurement specifically for that, but they will allow you to do things like an FFT, fast Fourier transform, on the analog waveform to give you the frequency domain representation of the signal from which you could calculate things like THD and that kind of thing.
So that's we talk about oscilloscopes are things that show you the modulate. Well, tell me if I'm saying this right. They show you the modulation of voltage in the time domain, meaning across time, whereas something like a spectrum analyzer shows you in the frequency domain. Instead of you're not seeing it by time, you're actually seeing where the modulation happens by where it is in the spectrum. Yeah.
So another way to think about it is that in both cases, the vertical axis is representative of some kind of amplitude, either voltage or power. And in the scope, the horizontal axis is time. In a frequency domain, or in a spectrum analyzer, the horizontal axis is frequency. And by similarity, an FFT of an analog time domain waveform results in a output where the horizontal axis is frequency. So it represents amplitude vertically versus frequency horizontally.
Okay. So I'm actually just curious because, I used to build, I didn't design them. I followed other people's plans, but I used to build analog audio amplifiers, based on like the LM chip amps and things like that. And, measuring that kind of thing was like, oh, you got to buy a really expensive audio analyzer. I didn't realize that I could actually measure total harmonic distortion with a scope. So that's something I need to look into.
Yeah, I mean, it's tricky to do because you've got to set up the FFT to give you, what you're looking for. And then if it's total harmonic distortion, you've got to be sure you're only looking at the harmonic components of that 1 kilohertz. So you've got to make sure you get, look at the right peaks on that FFT result. And then you'd have to then run a calculation of those, of the magnitude of those peaks with respect to the fundamental signal you're looking at to actually calculate THD. I'm not saying it's an easy thing to do, but it could be done.
Oh, okay. Sorry. Well, then I'll lower my expectations.
Okay.
Something to point out also, we're talking about this where this is another example where having multiple inputs could be helpful because in the case where you are injecting a 1 kilohertz signal into something, you may want to monitor that signal because maybe you can vary the amplitude or whatnot. And then also you can monitor simultaneously like the output of what that signal looks like coming out of an amplifier.
Yeah. And the thing is like if you're looking at the sine wave on the scope, at what point can you start to see distortion? And I think I did a video on this a while back too. I was more thinking about it from an RF standpoint, but it certainly holds, at audio as well. And I think I kind of figured out that if you got, I'm trying to think what the numbers were. I think if the second harmonic was down by 30 dB, and I forget what that's going to work out to in terms of THD, but if the second harmonic was not down by more than 30 dB, you'd start to see it on the sine wave, and that's a pretty significant amount of distortion. Okay, so it's tough to see the THD just by looking at the sine wave. You really have to almost go to the frequency domain to do it.
All right, so bringing it back to features of digital scopes, we've now talked about some of how the data is collected, how the data is manipulated to render a waveform on the screen. Going back to kind of a hybrid, we talked about triggers. What are some of the types of trigger types you can set up in a digital scope? Like, what are some of the things you can actually trigger acquisition off of?
Well, it's almost better to talk about what you have on an analog scope first, and because it's relatively few. Okay.
See, I knew I shouldn't have said we were done with analog scopes.
But that's okay. But they're all common. Like anything the analog scope can do, the digital scope can do too. And that's typically triggering on, a level-based trigger, either on the rising edge or falling edge of a signal through a threshold of some sort. Okay. That's basically what you do with analog scopes all the time. And whether that is one of the input signals or it could be triggering on the line voltage, like 60 hertz. You want to look at something synchronous to the line. And then oftentimes you can either low pass filter or high pass filter the signal to the trigger circuit to accept or reject the low frequency or high frequency portion of the signal. Okay, and for analog scopes, there's some more analog scope trigger functions that could be a little more advanced for like TV applications to trigger on, a particular line or field in a scan frame of analog video. But that's not going to be used for what we're doing here. So from the analog scope standpoint, it's a pretty simple thing. It's a simple edge trigger. Okay, that's 99% of the time that's what you're using, and that's what the digital scopes have too. But now digital scopes also give the ability of doing more triggering on other aspects of the signal. Because as I mentioned earlier in the previous episode now, that the scope is sampling all the time. The trigger is basically just saying, hey, flag that. I want to grab that thing that you just processed and keep that one. That's my event of interest. So that event of interest can be defined by a lot of different things, not just, a rising edge or a falling edge of a signal or crossing through a voltage threshold. You could trigger on oftentimes a particular width of a digital pulse. Hey, I want to trigger when this pulse width is greater than this or less than this. Or I want to trigger on if I get a glitch, a little narrow little glitch that goes on. Or if my digital signal doesn't quite reach full excursion. And a good example of that, if I've got multiple devices connected to a digital bus, and then one device tries to drive the bus low when another device tries to drive the bus high. It's called bus contention. And oftentimes that'll lead to the voltage being somewhere in the middle, okay, instead of being a logic high or logic low. You can set up digital scopes to trigger on that condition. So it can really be helpful to isolate particular troublesome events like that. But one thing I wanted to circle back on a little bit of triggering, just a more basic topic, because it's another one that's oftentimes misunderstood, is the concept of auto triggering. So is that a topic of confusion you think we ought to clear up?
Sure.
Okay. So unlike the auto setup button that I almost admonished you for talking about, okay, auto triggering isn't the same thing. It doesn't automatically set up your trigger for you. Okay. Let's say you set up this trigger condition and you set it up wrong. Okay. And the signal never meets that condition. Well, then you might say, well, I'll never get a trace on the screen, right? So I don't know what's wrong. So, very early on, scope manufacturers realized that this is a very real possibility. You set up you don't have the trigger control set right, and the screen is blank. You don't know what to do. So what auto trigger does is it waits for a little period of time to see if the trigger condition you set up happens. And if it doesn't, it just initiates the trigger by itself anyway. Okay, that's auto trigger. What that does is it always provides you feedback on the screen, so you're touching your voltage right, or you're really connected, and the scope's not frozen, you're not way off in the weeds somewhere. So that when something does happen, you might then go and readjust your trigger to make it work. So auto trigger is almost like a safety heartbeat. That if you don't get a trigger event within 100 milliseconds or 50 milliseconds, it shoots out a trigger anyway, so you get a trace across the screen or you get a waveform that shows you something. So it doesn't automatically set up the trigger; it just auto generates a trigger in the absence of a real one.
Okay, so
a qualifying one.
It's a safety net.
It's a safety net, exactly. So I just wanted to kind of clear that up. And again, I did a video on this too, because it is like people that, I just set it on auto trigger and it's not, my waveform is not synchronized. Well, because it doesn't automatically synchronize to your waveform. It's just telling you that you haven't set up the trigger properly to synchronize on that waveform right now, but it's giving you the visual feedback so you know what to do. Okay.
Okay. So we've talked about capturing. We've talked about how to initiate the capture. We've talked about some basic I'll call it statistical or metadata about, the frequency, the rise time, things of that nature. One of the things that I know about my scope is that there are advanced functions available where you can say, for instance, combine two waveforms and display the product of them, or you can actually use some low-level logic to put the two together and then look at what the combined product of those things are. They can do integration and differentials and all kinds of fun math stuff. What are some of those functions and things to look for?
Hey, great question. And probably the first and foremost important one is to be able to take the difference between two waveforms. And I say, well, why would I ever want to do that? Well, it kind of goes back to something we mentioned in the previous episode that, a scope measurement is essentially a single-ended measurement with respect to ground, right? Because one end of the scope probe is ground. So you're always measuring voltages with respect to ground with any given channel. What if I want to measure the voltage across a transistor from collector to emitter? Well, I can't just put the scope probe across that because then I'd connect one of those two nodes to ground. I don't want to do that. But if I use two probes and probe one of them on the collector, the other one on the emitter, and I subtract the two, that's the same thing as measuring across that component, right? Just like if you did it with a multimeter. So by being able to take the difference between two channels, you essentially can get a floating or differential measurement across a component. This is the only math function, or one of the only math functions that the analog scopes would do. And they didn't call it subtraction, they called it add and invert. It would invert one channel and add them together, which is the same thing as subtracting it. And that's why your scopes had that old add and invert, capability on the analog inputs. The digital scopes, you can do it mathematically, so it's a very simple thing. Just subtract the two channels. So that's one reason why you'd want to use that math function. Another reason you might want to use some math is, let's say you're probing some node that is proportional to the current flowing through a circuit, and probing another node that's proportional to the voltage going to that circuit. If you display the product of them, you're essentially showing you the power that circuit is consuming instantaneously, right? Or something representative of that power.
Wow.
Okay. So, those simple, just, arithmetic measurements or arithmetic operations can be really powerful. Some of the scopes will allow you to plot trends, of a particular thing, like show me the trend of the frequency measurement. So you can see how the frequency is varying over time across that waveform. Some can do integrals and differentiations, like you mentioned. So it all depends on what information you need to gain from the measurements and how that, to determine which of these mathematical functions that you need. A very common one that we mentioned already is a fast Fourier transform, FFT. It's a fancy mathematical operation that shows you the frequency domain content of a waveform. Like if you looked at it on a sine wave, ideally you would just see the noise floor and a peak at one frequency, and then the rest of the noise floor again. If you looked at a square wave, you would see a peak ideally at the fundamental frequency and the odd harmonic frequencies, 3 times, 5 times, 7 times, 9 times, etc. of that signal. So it's a poor man's spectrum analyzer in that sense. Okay, so that's something that you find on most digital scopes these days, is that functionality, is to be able to kind of flip domains like that. So again, a lot of it is just going to depend on what information you're trying to extract from your circuit. And many people will have a digital scope and never ever use a math waveform. Okay, but the difference waveform is probably between channel 1 minus channel 2 or vice versa, is probably the most common thing to do to be able to make a measurement across a component.
George, have you ever used these math functions on your digital scope?
No, is the short answer.
Yep.
For me, most of the things I do are pretty simple. I'm typically looking at an audio channel and trying to figure out why the thing isn't amplifying, or what the audio filter looks like, or why it's distorted. And mostly I'm just eyeballing the waveform. So I think for myself, I use a fairly simple subset of the features of the scopes. So, a lot of it. Go ahead.
The funny thing is I look at sometimes some of the math features, that some of these scopes have, and I could sit there and part of I think about why is that there, and the only good reason I come up to is like, well, because they could. It's like there may be one guy in 10,000 that needed that measurement or that math function, but it's like, why else would anybody ever want that? But like I said, a lot of it is there probably because, well, we could do it. It's just math,
I'm sure there's a bit of that. I think there's also in the industrial electronic world, there's more complicated corner case things that people are looking for, and probably those things are very helpful there. But I think that's really a level beyond what most hobbyists are going to be concerned with.
That's true. And I think for the hobbyists, to me, the two that are going to be probably the most important are the simple difference measurement to make a differential measurement across two arbitrary locations in a circuit that are, referenced to the same ground, and an FFT. Those are probably the two most common ones that will probably be used by most hobbyists, if they're going to use any at all.
Yeah, actually, the FFT is pretty handy. I certainly have used that before, but that and the display of the data, as I mentioned before, showing you, let's say, the average voltage or the frequency, that's actually pretty handy. But
yeah, that's more of a measurement rather than a math function.
Yeah, exactly.
The math function will result typically in a trace, whereas a measurement will result in a number.
Exactly.
Another thing that just came to mind while you guys were talking about is, I know, both analog and digital scopes have options for coupling. And you'll generally see like DC or AC coupling. Help explain what coupling means.
Great. It's another great question, another point of, confusion for people. Because if you think about, okay, I've got an old Simpson 260 analog voltmeter, or I've got my Fluke 87 DMM, and I can put that in AC mode or DC mode to measure AC signals or DC signals. Okay. That is not what the coupling control is on a scope. Okay. The coupling control basically says, how am I processing the signal from the probe to the scope input? And there are many times where you will use DC coupling to look at AC signals, or you might look at AC coupling when looking at DC signals. So why would I want to do that? Well, let me give you an example. Let's start with the case where I'm looking at a DC signal with AC coupling. Let's say I'm looking at a power supply voltage, 12 volts, 13.8 volts, okay? And I want to look at ripple on that. Well, if I put my probe on there and I DC couple, and I set my scope to, say, 2 volts a division and move my position so that ground is down near the bottom, 12 volts is going to be 6 divisions up. Okay, so, but if I've got 100 millivolts of ripple on there, at 2 volts a division, I'm going to barely be able to see that. So if I change my sensitivity to be 1 volt a division, now the waveform wants to be 12 divisions up from ground. It might be above the top of the screen. You might be able to bring the position control down to see it, but still now trying to see 100 millivolts ripple with 1 volt a division, you're only going to see that's only going to be a tenth of a division big. Still may not be able to see it. So you crank the sensitivity again, and now you run out of room. I can't bring the vertical position down far enough to bring the signal back down onto the screen. Okay, because now it wanted to be maybe a 10 or 20 divisions above the top of the screen. But if I AC couple the signal, okay, the DC portion will get blocked. So the signal will surround itself around ground, and now I can make the sensitivity whatever I want it to be and only see the AC content or the ripple on that signal. So this is where AC coupling can be really useful for looking at a DC signal.
Well,
Okay.
and similar, I would assume then for audio amplifiers where you do not want to pass DC into your speakers, you
There you
would do the inverse of that by looking at the sine wave that you're pumping through the amplifier, but DC coupling it to try to find DC products on the signal.
That's one great example. Another example is maybe even further up in the amplifier chain. You might want to see how close is the peak or trough of my analog signal getting to my power supply rail or to saturating a transistor. Okay, so as you'd say, well, if I'm DC coupling, I know my supply rail is 15 volts. If the very peak of my waveform is going to 14.5 volts, you've only got a half a volt of headroom before you start clipping. Okay, so by DC coupling, you can start to see how your signals are living within either the supply rails or bias rails of a particular design.
Wow. I have been using my scope so wrong. Because the nice thing is about my Regal is that you were talking about, spinning the dial to move the position up. Mine will let you do that all day long, but as you continue to zoom in, you have to turn more and more and more and more, to try to walk up to where the signal is. And it's really annoying. And
eventually you'll reach a point where there isn't enough offset range to do that. Okay, so think about the AC and DC coupling controls are just that. They're coupling controls, not modes.
Okay. Now, we have covered in pretty good detail the majority, I think, of the common features you're going to see on at least the lower level, entry level digital oscilloscopes. I know there are a lot of specialty features. For instance, my Regal on the back has there are ways you can trigger the scope as part of an external test suite, and you can actually draw an envelope that it will register an error if a waveform goes outside of an envelope. And that stuff is, I think it's cool, but probably well outside of the realm of use for the average hobbyist.
Yeah, there's lots of advanced features and advanced measurement capability that are in digital scopes these days, partly because the technology enables it. And, many of the scope manufacturers try to incorporate features that help designers and things like that, make faster decisions, faster measurements, reduce the amount of times they have to do calculations. So the more measurement capability that can be added into the instrument, the more efficient that particular designer can be in completing his design work. So everything from, like you said, mask testing for an envelope or something like that is one example. We've got scopes that have got advanced power measurement applications to be able to look at the efficiency of switching regulators, for example. So there's lots of these types of advanced measurement capabilities that there's huge laundry lists, especially as you walk up the performance scale of scopes that can be added to these digital scopes as usually typically as options that can be licensed to do some very advanced measurement and compliance measurements and things like that the average hobbyist would never use.
You bring up another good point that we haven't addressed, and thinking earlier, talking about the analog scopes that we talked about, where you buy an analog scope and it's 100 megahertz, then you're stuck with 100 megahertz. But a lot of even like the Regal scopes, there are some models that you can buy that you may buy at 100 megahertz, but you can actually buy license keys to unlock 200 or 300 megahertz worth of bandwidth, and you're out the cost of the software key and not having to buy an entire new scope.
Yeah, and certainly there's a lot of scopes that you can do that, and also even add features. I mean, like you said, you could buy a scope that's got 4 analog channels, and then add an option key that turns on the digital inputs, and now it's a mixed signal scope.
Yeah, actually, in researching this episode, I was very frustrated. Granted, the scope I have, I bought probably at least 2 years ago, maybe 3 years ago. And then after that, they released a mixed signal version of it. And now they make the Plus model, which has all the mixed signal hardware in it. But when you buy the actual probe kit, it comes with a license key to turn it on for like an extra $270, which is pretty reasonable for a 16-channel logic analyzer.
Sure.
So, I mean, that's the one downside about these Chinese scopes. And actually, I don't know, a lot of electronics, if for our listeners who own a Baofeng, there's the 400 versions, because every week they've fixed one little thing or updated one little thing, and boom, you have an entire new version of the product.
Right. That's like the beauty of software-defined radios, is that you can change firmware and it's a whole new radio. So
and it is interesting from a design perspective, though, that at the end of the day, these scopes that you're unlocking more bandwidth with a software key. I mean, whether regardless of which scope you buy, they're all the hardware the same. Same scope, and there's economies of scale in manufacturing. But and I know sometimes it's frustrating to know, it's like, I know my scope can do this, but because of stupid software.
Right. Yeah, but it's one of those things that, like you said, if the manufacturers had to make 5 different versions of the scope, you wouldn't get the scope you bought at the price you bought it, because there wouldn't be enough volume in that particular model. So the reality is that by using the economy of scale to bring the hardware costs down, the manufacturer can recoup some of that development activity. For those that need the extra capability that they built into it, they pay for it. Not everybody pays for it.
Yeah. So. And I mean, in some of those features on my Regal, and I'm sorry to keep using this as an example, it's what I have.
Yep.
By default, it came with 12 mega something memory.
Yep.
I forget what the mega samples.
Yep.
Yep. And you can unlock it up to 24.
Right.
There in the triggering options, as we kind of mentioned in the last episode, I could have it trigger off of specific I2C things. That was, an add-on. And also the protocol decoder was an add-on, which, again, I've never really gotten to work very well. And after buying a computerized logic analyzer, it is a much better tool to work with than trying to do that on a scope.
Sure.
Of course, and as you spend money, I mean, these features become better. For instance, as you move up in that product portfolio, and I'm sure the same goes for tech, that your computer integration, by being able to plug this into a computer and use software to get data out of the scope into something on the computer, be it from the manufacturer, or there is a product out there that's very common for running these things called LabVIEW.
Yep.
And you can build profiles and custom automation, all kinds of stuff to get data out and do things with it, and make decisions based on it.
Yeah, and because the programmatic control over the instruments. I mean, a lot of the scopes actually you can hook up an Ethernet port to them. Hook them up into Ethernet, put them on your network, and then use your web browser to drive the scope. So there's a web browser built right in, or web server built right into the scope, so you can actually just plug it on, put it on your network, and control it or view it from anywhere on your network. That's just kind of just remote operation of the scope. But then, of course, there's the whole issue of a programmable operation or programmatic control over the instrument. LabVIEW is an extremely popular way of building an application where you can automatically collect measurements, change scope parameters, make some other measurements, so you can completely automate the process of doing testing. And that's very often done in manufacturing sites to test products, where they don't have somebody sitting there twiddling the knobs on a scope and making measurements and recording the results like the old days. Now you've just got programmatic control over the instruments, collecting all the data, and the whole thing is just automated. And, LabVIEW is what I would call kind of a higher level, type of programming environment, where you can manipulate various blocks, high level blocks of measurement functionality and connect them together. You can also build applications from, just about any programming environment, C++, Visual Basic, Python, you name it, MATLAB. All these tools could be used as, for programmatic control over these instruments these days.
Which I noticed, just browsing through the downloads here on RegalSet. I mean, they actually give you a lot of I see .NET libraries that are basically the instrumentation communication protocol and some example code that you could get these into things, plus a lot of other code snippets and whatnot that would help you integrate with other tools. Again, probably way beyond what our listeners would ever use a scope for, but it's one of those things. It's like, hey, it's nice to know that feature's there in case I ever have a need or want to play with it.
Yeah, the doors are there, and that's what I tell even as a application engineer for Tektronix, and customers see all these myriad of features, and I say, the reality is that any particular customer, even my professional customers that I deal with, they might use 10 to 20% of the features that the scope can do. But the next customer down the block uses a different 10 or 20% of those features. So overall, everybody's using something, but just about nobody uses everything. So,
I hinted at the memory depth. Do you have a suggestion on what a good number is to look for that?
Well, the funny thing is, we talk about even the way George has been using his scope just as viewing waveforms. The reality is oftentimes, there are many, many times where you never use any really extended memory at all. Even because Tech still is actually selling some scopes whose design is close to 20 years old that only have 2,500 sample points, 2.5K. That's ridiculous in today's world that, scopes that, you got a brand new scope you can buy off the shelf. It's only got 2.5K of memory, but that's the way it was designed 10 years ago. And for many, many customers, that's all they ever needed. And they've written these scopes into test sets and things like that. And they do exactly what they want. And 2.5K is enough because you never have to do anything where you needed the extended memory. So the thing is that for a lot of people, especially just looking at as a waveform viewer and to make sure the signals kind of look right, you don't really need the extra memory. When you start getting into things like where you're talking about doing longer captures because you're trying to capture a communication channel like an I2C bus or a SPI bus, or looking at a longer term variation but of signals that are moving quickly, that's where you're going to start to need more memory. Or if I need to have a higher sample density, for one reason or another to accurately represent a rise time on a digital signal or something like that, and a longer time duration, that means I might need a higher sample rate and I'll need deeper memory so I can capture enough record in time with sufficient sample rate to resolve what I need to look at. So what's a good number? Hard to say. It might be, 10,000 points, 100,000 points might be all you need. I'll tell you that I've got a digital scope on my bench that I use all the time. It's an MDO 4000, and it's got up to 20 meg of memory. And the vast majority of time, I'm using 10,000 points. I'm using a 10,000 point memory, and I don't need any more than that. There are instances where I do need more, higher resolution, and I'll dial it up when I need it, because usually what happens if you say, okay, I want to use the full, 20 meg, or I want to use the 12 meg that I've got, or something like that, the scope's got to do processing on that number of data points, and that slows things down. So it's only when you need the extra sample depth that you are willing to pay the price for the slower processing time in order to be able to utilize it. So I would say for most of the poking around, debugging, looking at waveforms, you're probably only using 10,000 points or less.
Okay, and the last spec that I'll ask about is waveforms per second.
Yeah. Great. That's another great question. And that kind of feeds into just what we were talking about, is that processing delay. And a lot of this kind of gets back to even from the very early days of digital scopes. One of the biggest complaints was that there's a lot of dead time between triggers, because in an analog scope, you trigger, it kicks the sweep off, you get a waveform that sweeps, and then the horizontal oscillator in the scope quickly is reset back to the left side of the screen, and it waits for a trigger again. So you can get hundreds of thousands of waveforms per second because all it's doing is kicking off the sweep that fast. The digital scopes, when they first came out, they would trigger, they'd get that set of samples and put them into memory, and then the engine inside the scope had to take those numbers, figure out how to display them as a waveform on the scope, wait for the scope display's refresh time to come up to paint a new picture of the waveform on the screen. And then it would rearm the trigger circuit again. So you'd be lucky if you can get more than 20 or 30 waveforms per second, okay, because that was kind of the display update. Okay, that was going back to the early days of analog scope or digital scopes, digital replacements of analog scopes.
So this is, I know we're not talking spectrum analyzers, but it sounds like this is similar to the difference between the resolution bandwidth and the video bandwidth.
Kind of. Those two things are a little bit different, but they do different things. But it really does come down to what's happening between those two trigger events now on that digital scope is that the scope is really not looking at anything. It's blind. So the duty cycle of how often you're looking at a signal versus what it's really doing is really quite low, can be quite low.
By the way, you're allowed to flat out tell me I'm wrong.
No, that's okay. The difference between resolution bandwidth and video bandwidth is pre-detection and post-detection filtering is what it comes down to.
Okay, never mind. We won't go down that hole. We were going to do another episode on spectrum analyzers in the future, so we'll save it for that.
Okay, and I've got a video on the difference between RBW and VBW, so if you want to go watch that, it's there too.
Outstanding.
Okay, so there's a video for that. I'm going to keep saying that.
No, that's fantastic. That's why we reached out to you to bring you on, because I could not think of another person who was both friendly and would know more. So this has been,
and it's not on the other side of the world. So.
Well, and actually, this isn't a denigration against Dave, but I mean, Dave is very clear that he's busy doing his own thing, and unless he's not going to do something else unless it's really interesting for him. So, and I don't hold that against him because I have very limited time. It's like I wasn't kidding when I said my ham radio these days is sitting in front of the SM7B in front of my face right now doing podcasting, not working HF.
Right. And Dave is not a ham. And like I said, his channel is an order of magnitude more popular than mine. So he certainly has a lot more demands on his time than I do. And that's that way. Anyway, so we're talking waveform capture rate. So as technology has has progressed to improve digital processing speeds and things like that, we've gotten to the point where we can make these scopes acquire triggered acquisitions much faster. Okay, so what in effect it's doing is reducing the blind time between triggered events, so that now infrequent events can be seen, or you can get a more lively representation of a waveform, with more quickly changing events. Now, obviously, because we're looking at essentially an LCD monitor on these digital scopes now, those LCD monitors are only refreshed, maybe 30, 40, 50, 60 times a second, right? 60 hertz or something like that. So why does it matter if I get more waveforms than that? Well, the reality is that it'll overlay those waveforms, and because you're not just looking at a single row of pixels on a waveform, it's usually a cloud, of pixels, or I should say a vertical column of pixels that is intensity modulated based on the overlap of all the waveforms that were collected since the last display update, right? So it's trying to emulate what the analog scopes did naturally. So the more waveforms per second you have, the more likely it is that you will see infrequent events and be able to maybe more smoothly see variations as they happen. So what do you really need? A few hundred waveforms per second is good. A few thousand, 10,000, 20,000 is much better. But is 50,000 or 100,000 that much better than 10,000? In most applications, no. Okay, but you want something that can do at least a few thousand waveforms a second. If you're looking for digital glitches and things like that, then you really want a higher sample rate, because then if you start to see anomalies, you might say, "Oh, it looks like I got a little bit of bus contention that happened right there. I just saw it flash on the screen." Or you can set the scope to be in like infinite persistence mode, so it always shows everything and keeps it on the screen. You might start to see an anomaly. Once you see it, now you can set up a specialized trigger to trigger on just that thing, so that now you can isolate that particular event. And that's where a high waveform capture rate can be helpful, because it can help you to see these various little anomalies that are happening that arms you with the knowledge to set up a more intelligent trigger to zero in on those particular types of things.
Okay. So I have exhausted my list of things to even ask you about digital scopes. George, is there anything we're missing?
Well, I think in terms of features and functions, I think we've covered it quite a bit. There's some interesting different kinds of scope form factors that we might want to talk about for a couple minutes.
Sure.
So what I'm thinking is the traditional scope is the box with feet and buttons and knobs and sits on your workbench. But I think over the last 5 or 6 years in particular, the number of scopes that are headless, that are the oscilloscope electronics, but using a PC as the user interface, that's grown a lot. I've seen miniature scopes you can fit in the palm of your hand. I've seen some kits that are very simplistic kits you could build for like $30. So maybe we could take a minute, Alan, and dive into that space. And I realized that certainly those kit things are like way down the feature and performance spectrum. But let's talk a minute about a traditional boxed instrument versus a headless instrument. What do you think about that?
Well, the other thing to remember too is that going from the analog scopes that had the CRTs in them, the scopes were really deep, and most of these, kind of what I would call just your mainstream digital scopes, until you get to the real high performance stuff, the boxes are really shallow, so now they can fit on your bench and you can put what you're working on in front of it, so that really helps a lot. But these displayless or like USB based oscilloscopes are out there. Personally, I'm a fan of buttons and knobs. So personally, and this is just my own personal feeling, is that I'm not really a big fan of USB-based scopes for a couple of reasons. One is that, again, I'm a fan of having the buttons and knobs that I can go and control and adjust rather than using my mouse and keyboard. Number two, I don't have a computer on my bench. Maybe I'm too old school or whatever. I don't have a computer on my bench where I do my work. So I don't want to have to bring my laptop down there to go do that. So it would be less convenient for me to use a USB-based scope. And third is that now I'm introducing the fact that my oscilloscope or my expensive laptop is connected to an instrument via USB that on something that I'm testing. Is that somehow going to be injecting noise into the thing I'm testing because of its proximity, because the grounds are common and this kind of thing? So there's a couple of reasons why I'm personally not a fan, because now if I was doing a lot of microcontroller things and my computer was there anyway and I'm always sitting in front of the computer with my mouse and keyboard and I just want to pop up the scope application, like I'm sure you do, Jeremy, with the Saley logic analyzer, then it might be a great solution for you. There's a lot of companies out there like, Picoscope and people like that make these USB-based scopes. And they're, and again, it's probably a bit more if you get what you pay for. If you get one of these $30 or $50 kits, then you're going to get about that level of performance. But there are some out there that have got good performance. But you've got to take a look at, is there any more limitations on input voltage range and that type of thing, and noise, and versus a standalone instrument. But so I'm not going to completely disparage them. It's really more of a personal preference on my side than anything else. These other form factors, like these little kits where they've got little LCD displays and everything all on one board, I think they're great, probably more waveform monitoring type things, because those displays often don't have the resolution of even your basic entry-level digital scope. And they're probably not going to have, like as you said, the bandwidth, the flexibility of using different types of probes and that kind of thing. But for certain dedicated applications, if you just want to monitor a waveform, that might be perfectly adequate. Again, it's like I only need that $30 worth of functionality for this particular application, but I wouldn't want to be using that as my main scope on the bench type of thing.
So that makes sense. I think some of the headless scopes, you do get kind of a price advantage where you might see similar specs at a lower price point, but then you do have the performance issue perhaps with the data transfer to the PC, and the refresh rate on the display is not going to be as fast, I've seen. So I've got some of these low costs, let's say not the professional headless scopes, but kind of the lower end ones.
Okay.
And you'll change the sweep frequency, and it doesn't always react immediately, not like you expect a real instrument to react. So at the lower end, you're probably going to compromise something. But
the other thing too, on the other hand of that, is now you've got the power of your PC doing the processing, and there may be more functionality that you can get, per buck.
Well, that may be
than you'd get on a basic, entry level, benchtop scope, because now it's just software in the scope instead of firmware somebody had to write on the instrument. So there may be more flexibility and more display resolution and things like that. So there may be some trade-offs on that side that make these headless instruments a bit more attractive.
Well, and maybe it's like any new technology where the first few generations are somewhat usable, functional, but they're not great. And then over time, like digital cameras, when digital cameras first came out, it was novelty, but if you want a good picture, you'd use film. And today, who shoots film? I mean, that's the novelty. So maybe over time, we'll see more and more higher performance scope modules moving towards the PC. Although, you do sort of miss the buttons and the knobs.
Well, I think where you're going to see that too, and we see it on the professional side as well. There are people that make, professional, headless scopes that fit in like a Pixie card chassis or something like that, and they're geared for manufacturing operations where nobody is physically sitting there looking at a waveform. Right, the computer is grabbing data, making measurements, and nobody cares that there's a display on it. Okay, so there's at the other end of the spectrum, so to speak, there are applications for these headless types of instruments as well.
Sure, that makes sense. So I think that's the only other area, Jeremy, that I really want to touch on is these different form factors.
Well, and I'll mention a couple of products. And I'm not endorsing these because I haven't used them, but you mentioned Picoscope, which I think is probably one of the more ubiquitous USB powered data acquisition decks for an oscilloscope type purpose. There's another company that I became aware of called Bitscope, and they make a little bit lower end stuff, but I became aware of them because they have structured, going back to this industrial usage, they also sell a line of Raspberry Pi cluster hardware, and I build Raspberry Pi clusters as a separate hobby. And I was looking at their stuff, and the point of their clusters is to be able to build a giant test frame where you're hooking up their Bitscope acquisition devices and having the Pis basically act as front end, like stage 0 data aggregators to pass that data somewhere on down the line for analysis, which is really cool. But in addition to just being an oscilloscope, a lot of these devices are giving you the benefits of also having the logic analyzation. And then some of them even have little spectrum analyzers in them. Some of them have both RF and electrical function generators built into them. Like, George, what was the green device we were talking about a couple weeks ago?
I don't recall.
Is it Digilent?
Well, Digilent they do make a scope module, which is
they've got a
multi-function
module, yeah.
Right.
And that even has a very low current, like 5-volt power supply built into it. So it's interesting, because one of the things that our listeners aren't going to go out and spend, thousands or maybe not even hundreds of dollars on a scope. And so, introducing somebody to the world of this, the way that for me, my first multimeter was a $20 Craftsman purchased 20 years ago. And now I'm lucky to have a Fluke 287. An entry into this, to being able to have this capability and to understand it may very well be one of these $100 or $200 USB, mixed function devices.
Sure, and it may not be the most convenient thing to use or the most flexible thing to use, but it's better than having nothing. So, and I think that's the same thing. There are, I've just pulled up the Bitscope webpage here to see what you're talking about because I wasn't familiar with them. But again, this is the kind of thing where for some applications, this is the right tool for them. Whether it's you're going to be doing some automated things, or you're not doing a whole lot of heavy duty debugging where you're always interacting with the scope and you want to make quick changes. These could be the right tool for those types of things where you've already got a computer there to do a lot of the work that you're doing on your bench, and that's for some people this is the right tool. So I would say it really comes down to how much are you going to need to interact with the instrument, and how convenient or inconvenient will that be to be using a mouse and keyboard to do it rather than reaching up and spinning a control.
Well, one other thought on these smaller USB connected devices is the size of that unit is really tiny. And believe it or not, there's actually some people in this world that don't have an enormous test bench at home. And sometimes you have to set up your workbench on the kitchen table. And if you're dragging out the old 465, great as that might be to have, it might be much more convenient to have a little puck that's plugged in on USB. So there's probably other kind of, home-friendly reasons why you might consider some of these smaller USB-connected devices. And the fact that you've got, to your point, you've got something as opposed to nothing is an enormous leg up.
Absolutely. And in fact, even at Tektronix, we're seeing a move to that area as well. And Tech has got, a line of USB-connected signal and real-time spectrum analyzers, and are actually really popular, with a lot of the professional customers, because now, one of the problems with a lot of the higher-end performance equipment is that, essentially these things are specialized hardware, and in many cases, in most cases these days, there's a PC built into there with a user interface that's running on the PC that talks to all this dedicated hardware. So you buy, this $50,000 spectrum analyzer, you're buying a PC and all this hardware that's in it. And then 2 years down the road, the spectrum analyzer hardware is still perfectly good and usable and does everything you want, but you're dealing with a PC that's 2 years old and without a really good way of updating it. So the disaggregated model of things allows you to upgrade where all the processing is happening while all the acquisition hardware is still valid.
Well, and that's exactly the model of these modern SDRs like the Flex or the Anon.
Exactly.
Again, it's an RF deck, and all the feature, it's just a data acquisition tool, and the software and whatever platform you plug it into is really where the flexibility and power comes from. I've actually had going back to the $40,000, $50,000 techs that are basically a Windows machine in a box with all the A to D stuff. There was a guy in my club who did. He was basically a field engineer for Harris and would go out to sites and help customers figure out why they were having RF problems. And so he would sometimes bring his equipment out to the parks and let people hook their antennas up to it and use it as, the most expensive antenna analyzer you were ever going to see.
Right. Yep. And that's a lot easier to do with a smaller disaggregated instrument than a big box with everything in it and a display.
Going back to because I enjoy the knobs on the scope as well, but one of the things that is interesting, because oftentimes we'll talk about what do you get when you spend more money, and of course we've talked about all the different specs. You'll get more bandwidth, you're going to get better A to D converters, you're going to be able to have more channels with more sample rates and things like that. But even on the Regal at the 1000 series, I have 24 megapoints or whatever the measurement was to look through, but I have an incredibly small knob that has no way to increase the rate of jogging to actually scroll through data. And so even though it can decode protocols, it is absolutely an atrocious tool to do it on, because it takes forever to scroll to read a single string.
Right.
And that's if you move up to the 2000 series, they actually have navigation tools and search functions built in so that you can actually more easily and readily use that information.
Right, and those are the kind of things you get. I mean, and you can search and mark areas in your memory of interest, and then quickly move from mark to mark to mark. That's one way of doing it. We've actually got a pretty neat technology that we've got on a lot of our mainstream scopes now. That is when you're zoomed in on a waveform and you want to pan back and forth through that record. The control is a lot like the old shuttle jog on the old VCRs, where it's a spring-loaded knob that always returns to center. And the further you turn it from center, the faster you move. So you can scroll through 20 meg of memory in a half a second. Right, so you can, if you just turn the knob 90 degrees in one direction or 90 degrees in the other, and then as you work your way back closer to center, the rate of that it scrolls back and forth slows down. So it makes it very easy to kind of rapidly move to an area and then slow up and move around to get to the area you're interested in. But because of these types of things where, we've all been frustrated by having scopes where you've got a lot of memory, you capture it, you zoom in on an area, and then you're taking your position control and just you want to put an electric drill on it and spin it to get to the other end quickly, So.
Yeah, that's an 18-volt jog wheel.
Yeah, great. So
the DeWalt jog wheel.
There you go.
Actually, to be fair, one of the things that part of the reason I think that especially in the hobbyist market, these Chinese manufacturers have been successful at is, of course, obviously that, like you said, they bring a lot of capability, a lot of features, a lot of bells and whistles that may not be the most accurate. They may not be perfect. There may be some trade-offs. But for a guy like me who just wants a scope on his bench that he's using occasionally, it's more than fine. But am I correct in remembering that, Tech started introducing some, lower end scopes kind of aimed at probably maybe a little bit above hobbyists, but something that was still within the realm of affordability?
Yeah, there are. And, to be honest, Tech has never really focused on that, what I would almost call the ultra low price point. And it's just, Tech is kind of focused kind of on the industrial commercial market. But there are, some low cost scopes. And like I said, even these, we've got some scope platforms that are 20 years old that our professional customers still demand, and the price on those have come down. Actually, this was just a recent announcement last week. We've got a new TBS 2000, I believe it is, scope. And I think they start, sub $1,500, and you're getting a scope that's got like 10 or 20 meg of memory. So it's kind of more, kind of feature equivalent to the lower cost, like the Rygols and things like that. But that's only a relatively recent thing that Tech has been doing. It's just because it's not been an area of focus for Tech for kind of the prosumer or hobbyist market end of things. So, and part of the reason is that there's a different cost structure when you get into kind of the like the Keysight or the Tektronix realm of scopes compared to some of the other manufacturers. And I'm not going to pick on any manufacturer at all, but think about it this way, is that when, Tektronix or Keysight or, make our entry level scopes, the components that are used, like the display, is an LCD display that is an industrial rated display. It's going to work down at, over a wider temperature range, much more vibration resistance, whereas you go to the very inexpensive, scopes that you can find out there, and these are consumer grade displays from tablets and things like that, or that are consumer items, and are not going to have the reliability potentially as an industrial rated display. And the same thing holds true for the controls and other components, and that adds to the cost. And that's why, a scope from one of the top tier manufacturers for equivalent functionality is going to cost more than, something from, from one of the non-top tier type manufacturers. And, so it really comes down to, you get what you pay for, and sometimes you don't really see what that is, because you can't tell by looking at a brand new scope whether that's an industrial display or that's kind of a consumer, market type of display.
The customer.
Go ahead.
I should say the customer that's buying an industrial product also expects a certain level of customer service that you're just not going to get when you buy a box and get it, shipped from Amazon. It just shows up at, there you go. If you don't like it, tough it.
Yeah, and then the manual of what's there is not going to be as detailed and may not have the best English, grammar and things like that in it, and that kind of thing.
Right. Sorry, go ahead, George.
No, please.
I was just going to say, I was just looking at Tech Site, looking at that TBS 2000 you were talking about, and there is a TBS 1000 series where 30 megahertz, half a gigasample per second, 2.5K memory for 450.
Right, that's exactly what I was talking about. The basic scope acquisition hardware platform in that scope is close to 20 years old, but there's still been enough professional, industrial demand for that scope that, Tech has been trying to obsolete that thing for 10 years. But customers won't let us do it. So why not continue to sell it, right? They still want it. That's all they want. They don't care that we've got scope lines that have come out to replace that thing. they don't need the extra memory. Hey, I want this scope. This is what I've always used. This is what I want to continue to use. Keep selling it to me. So that's so there are lots of places and certainly lots of areas where that can go. And that scope, when the price of that has come down because we've long since repaid the engineering that went into making that thing. But people look at it and say, well, that's ridiculous. That tech is offering a scope that's got only 2.5K of memory when everybody else is orders of magnitude more than that. And the answer is, if nobody wanted to buy it, we wouldn't be selling it still. So it's
exactly.
Right?
Yeah.
It's not like that's all we can do,
Well, and life is different again in the industrial environment where you might have a test fixture that you want to use for a long period of time. And even though you can buy something better, you don't want anything to change in your test environment because
you don't want to change your code or anything like that. Yep, exactly right. So, like I said, someone looking in from the outside might say, that's a brand new scope with only 2.5K of memory. Why the heck would you do that, right? And that's exactly why. But like I said, now we're starting to see some of these things like the TBS 2000 that just came out that is kind of more addressing, hey, look, there are certainly a market for, these sub $2,000 type scopes that have got a lot of memory and features. So that's kind of the 2000 is really kind of the first. The TBS 2000 is kind of the first entry into that area that says, okay, hey, there's people that want this kind of scope too. Let's put something like that out there too.
So, is there anything else to be said about digital scopes?
Yeah, but but probably not what would be of interest to the guys who are trying to build a workbench or a hobbyist.
So that's why there's 180 videos that cover all the other topics.
Right. So
the one I think to kind of wrap up, one of the things that I think is kind of important, especially if you've never owned a scope, you don't know exactly how to use it. What is it when you buy a scope and it gets to your house? What are the first things you attach it to look at? What are the first things that you examine? Like, what are some things that the ham is going to have in their shack or around the home to go out and stick this thing on to start, getting data sources, basically?
Right. Well, I'll tell you the first thing that everybody should do that nobody ever does is compensate your probes.
I want you to know that I compensated my probes first thing because
Very
in all
good.
fairness, that little hook on the front of the scope was the very first signal that I could get the probes onto.
Yeah.
So,
and then you looked at it and say, wait, that doesn't look
looks,
right.
yeah, that's curved to the left.
And there you go. So there you go. Now you've got a signal to look at without even have to break anything else out, right? Boom, go do that. So that's the very first thing you can do is compensate your probes. Once you do that, now you can make sure that square wave looks nice and clean. You could look at some of the measurement features, adjust the time base, look at rise time, get a feel for how to use it, play with the coupling controls, the offset controls, to make sure you're comfortable with how to set up and trigger on the rising edge, trigger on the falling edge, see what differences that makes. So you can do an awful lot with that simple little square wave that's coming out of that. And
so I'm going to call that training wheels. Once I've gotten through that, what can I tear open? How can I just plug this into the PL 230 or 259 on the back of my radio and just key up into it?
No, I wouldn't do that. Well, you could do that once.
Make that the last thing you do.
Right. Well, it might be the last thing you do. So you might let the smoke out of something. But one of the very, very simple RF waveform monitors you can use if you have a transmatch or a tuner in your shack, like many of us do. Oftentimes those things have multiple RF antenna outputs, and we're usually not using all of them. Okay, so if you connect up a piece of coax to one of the unused antenna outputs on your tuner, and connect that up to your scope, and use the tuner normally, using it through your antenna. Don't set the tuner to go right to that unused input that you're just connected to your scope, but go to one of your antennas or to a dummy load. There's usually enough stray RF flying around inside the box of the tuner that you're going to couple some energy to the coax of that unused input, and that's enough to drive the input of the scope. And you could use that as a simple, monitor to look at the modulated RF output.
But like you said, make absolutely sure you don't have the full RF signal going to that antenna port on the back of the tuner.
Absolutely. If you connect up to antenna output number 3, don't switch it to number 3. Period. Don't pass go. Don't collect $200. Don't connect to number 3. So, because thing is, if you're transmitting 100 watts, you're going to be close 100 volts ish. That the scope may not like that. So, you can just couple just enough energy. If you're nervous about doing that, just hook a piece of wire to the front of your scope, just a little like an antenna. Maybe wrap a piece of wire around the outside of your coax 15 or 20 times and connect that to the input of the scope. There'll be enough leakage out of the coax probably to couple energy into the scope to see what's going on. Now, that may not be the best thing to look at first, especially if it's a digital scope, because of the issues I mentioned earlier about undersampling and aliasing of an RF signal. But it is something you can do very quickly. You might be able to, look at the audio output of, just hook up, where your external speaker is, hook up to the terminals of the external speaker. Make sure one side of it is ground. Maybe check that with your ohm meter first, and then use that with the ground side of your probe, and then look at the audio signal. That's another thing you can go look at. Just the audio output of the receiver, for example.
Actually, if you're going to do that, are you going to leave the speaker attached so that there's a load on the amplifier?
Yeah, usually. I mean, oftentimes you do that, or you might plug into like a headphone jack or something like that, or there might be an auxiliary audio output that might be used with a digital interface, like for PSK31 or something like that. You could probe that, because you might be wanting to do that anyway if you're going to design, a sound card interface between your PC and your computer to do, or your PC and the radio to do like a digital mode like PSK31 or slow scan TV or something like that.
Well, very good. Any other interesting things worth tearing apart and probing up?
It depends on what you've got. You could certainly look at your 12-volt power supply and maybe, again, AC couple it and turn the sensitivity way up to see how much ripple is really on that supply. If you're doing homebrew, things like that, then there's lots of things you can look at. You might want to look at the local oscillator signal going into the mixer, one of your conversion stages. It all depends on where your level of I banged the microphone. Sorry, your level of comfort. Of what you're comfortable digging into. But I would say use a bit of caution, because again, unlike poking around with the meter, the other end of that probe is a scope probe is ground. So you want to be sure that whatever you connect to, when you connect that to ground, that really is ground and it's not something else, because you'll take whatever that something else is and short it to ground, which your device might not like. So it just requires that one extra level of thought before you just start randomly poking around into things.
Okay. George, do you have anything else you think we should cover?
I am running out of topics. I think we covered it.
We've been at the 10,000 foot view, the 50,000 foot view, the 5 micron view. I mean, we've really been all over the gamut. I mean, and I'm sure it's going to be infuriating for listeners who really don't have a lot of background in this when we do go real deep. But like I always say, even if you don't understand what somebody's talking about, you at least walk away with things to Google.
Yeah, like I said, I think we've got a list that I put together of a subset of the videos that I've done that I thought might be useful for both training. Like a lot of the topics we talked about, like AC and DC coupling and 10x probes, and just auto triggering and all these various things. I've got a lot of individual tutorials on that. There'll be good links for people to go look at. But I've also got some just kind of ham shackish type of things, like how to measure capacitors and inductors with a scope and some basic parts, or how to build a simple little TDR to look for problems on coax, to do time domain reflectometry, or maybe you want to measure the velocity factor or the impedance of a hunk of coax that you have that you don't know what its impedance is. A scope can be useful in doing that when coupled up with a very simple little pulse generator that you can build for a couple of bucks. So there's a lot of resources, a dozen or 2 dozen videos that are just interesting things to get started on that might get you excited about going out and buying a scope.
All right, well, folks, our guest has graciously spent a lot of time with us over these 2 episodes, and I want to personally thank him again for coming in and giving us this time and this treasure trove of information, both on the show and also the vast YouTube library. You can find him online by going to youtube.com and searching for Whiskey 2 Alpha Echo Whiskey. Alan, thank you so much. Is there anything you want to leave our listeners with?
No, I certainly appreciate you reaching out to me. I've enjoyed this, and as you can tell, it is a bit of a passion of mine. So I'm really glad to kind of help your listeners out, and maybe building some of their understanding of a scope and how it might be of some value to them. And if you take a look at the videos on that I've got on my channel, and if you like what you see, subscribe to the channel, and you'll get a kind of a note each time I put something new up there. Or if you've got suggestions of videos that you'd like to see, I mean, that's where my video ideas come from, or from people that tell me, hey, I don't understand this, or can you do a video on this topic here? If it's something that that I find interesting as well, then it's more likely to bubble up to the top of a video that I might do in the near future. So I'm always interested in that kind of feedback from my standpoint, to help build a library that is useful for a lot of people.
All right. Well, thank you so much. And who knows, we might try to have you back on again when we get into spectrum analyzers. I bet we could get 3 episodes out of that.
We probably could. But hey, thanks again for having me on. I certainly enjoyed these 3+ hours that we spent recording today.
Thanks so much, Alan. 73.
73.
73.
All right, that'll wrap up our topic on oscilloscopes. At this point, we have given you, I think, just over 3 hours of quality content. If you have further questions, please check out Alan's videos on YouTube by searching for W2AEW. And of course, we will have links to all of them. Alan was kind enough to go through his videos and really hand select a lot of good primer videos on oscilloscopes. And I also want to apologize that, the conversation was just going so well. We didn't follow necessarily our normal format. And I promise you in our next episode, we will return to a slightly more compact and script following show. But again, thank you, Alan, for your time. And we hope to have you back on again for another topic in the future. So, George, what are we doing to return to normalcy next time?
Well, I don't think we're returning to normal exactly, but we do have a great show, because the next episode is an interview with Matt Berggren. And Matt is the guy from Autodesk who's in charge of the Eagle PCB software business and a bunch of other interesting things. And it turns out that while Matt's not an amateur radio operator himself, he comes from a family of hams, and he's been around ham radio and RF and all that for his whole life, and he's very interested in that space. And so Matt's going to give us his perspective on where he sees design and design tools going in the future, and how they're really focusing around the whole maker and home hobbyist space in addition to their commercial products. So I think it's a really interesting interview, and Matt's a delightful guy. You'll really enjoy it. So I hope everybody tunes in and listens to that episode.
And one of the things that's actually really cool about this episode is it has inspired potentially some other episodes down the line. So I can't wait to hear this.
Yeah, it's really going to be fun. Matt's an awesome guy, and I think you'll all really enjoy it a lot.
All right, and a reminder to everybody again, for all of your tools and your components, parts, and boards like Arduino and Raspberry Pi, you can check out our show sponsor, MCM Electronics, at www.mcmelectronics. Don't forget, you can save 5% off with the code RADIO5, that's RADIO 5, when shopping at mcmelectronics.com.
And also, when you're thinking about your next project and you want to do your first printed circuit board design, you really need to use Eagle. Check it out at www.cadsoft.io.
And we will return again next week with Q&A. We have several questions that have been kept up, so please remember to keep sending those to us. You can reach me online at jeremy@hamradio360.com, or find me on Twitter at KF7IJZ.
And you can reach me at george@hamradio360.com, or on Twitter at KJ6VU.
All right, thanks for listening. We'll catch you in 2 weeks. 73.
73 is all. Shakalaka laka. The whole idea was to come up with topics that you want to...
Start again? Okay.
Well, we're out of time.
We only
Thank you for listening.
we only had 10 minutes of recording to do tonight. 2.5 hours later. All right, let's try this again.